by Rodica Borcia on lubrication approaches for binary mixtures. He also comes from Brandenburgische University of Technology.
So, can I start? So I will speak about lubrication approaches for binary mixture. The work is done together with Professor Michael Besterhoff and with Dr. Rodica Borcia. And I will start presenting the statement of the problem, then the model, a little bit of the model evolution, the first model, other attempts, and the actual version. And then I will present numerical results, linear stability analysis, the 2D and 3D nonlinear simulation, also some 3D nonlinear simulation, but with the model without temperature gradient. So we have a two-layer system, heat it here and cool it here, and the surface is deformable. The first layer is a liquid mixture, and here is the passive layer, and I consider convection only in the liquid mixture. So here we have two mechanisms. One is destabilizing, so that the surface tension gradients due to the temperature will destabilize the liquid, and if this Marangoni separation ratio has the right sign and it's strong enough, the concentration will push the liquid again in the hole here and will be a stabilizing mechanism. And if we play with the relaxation times, and then we can expect also to have some oscillatory behavior because of this interplay of the two mechanisms, one stabilizing and one destabilizing. And we work on under the lubrication approximation, so the dimension in the vertical direction is much smaller than the deformation on the lateral deformation. Okay, we consider also gravity in our system, and the surface tension depends on both temperature and concentration. So for the first model, we consider the conservation of the of this quantity H, so of the total volume by constant density. That means the constant mass in the system, and usually we have here the mobility H3 over 3 nu, and this form of the generalized force, which is related to the chemical potential, and usually is took as double well potential with the left minimum for the disjoining pressure. For the concentration, we took the linear relation, which is written here, and we consider all the time in this simplified model that the concentration and the temperature vary linearly in the vertical direction, so the second derivative will be 0, so this operator here will be, we take only the horizontal part of this operator. Also here it's again written that the surface tension depends on temperature and concentration, and with this condition the current density of one of the components will look like this one. And now we want to be as simple as possible, so we take this mobility 1 and also the temperature directly proportional with the film height, and making in place of H we work now with the new variable U, and then we come to these two very simple equation. The first one is almost the Cahn-Hilliard equation plus an extra term for the concentration, and this is the equation for the concentration with L, the Rescald Lewis number. So it's it's took to be as simple as possible, the model, but still can explain some of the behavior. So we have two control parameters, the Marangoni separation ratio and the initial film height. And then we can obtain for very small or very high film height, initially film height, conductive state, and depending then on the separation ratio, oscillatory or monotonic behavior. So we obtain monotonic behavior for positive Marangoni separation ratio or for small negative one. Also, one can say that for small height of the film, drops appear in the system for higher height of the film. So holes are energetically favorable to appear. And here it's a 2D simulation starting from horizontal film with a very small perturbation, a random perturbation. And here appears 5 peaks initially, like in the linear analyze, say. And then we have coarsening, and finally we become a single drop. In the meantime, because this high is enough negative, we have symmetry breaking, so that's the concentration is lower here and higher here, and this concentration profile will drive the motion of this drop. So here I show the same in a 3D simulation, which mathematically is 2D, and also we can see that if we would look at the movie, that the movement of this side are driven for the concentration field. And here it's okay, this is some intermediary states. This is after a longer time, because I choose the initial height near 0. It's hard for the system to decide to be drop or holes. So these traveling stripes will appear in the system also from low concentration to high concentration. So it's here with line, it's the concentration field, and in contrast with the height. For the height, the lighter region means higher high. In order to have contrast for the concentration, I choose lighter line, lower concentration. Yes, lower concentration. So this moving of the stripe will be from lower concentration to higher concentration, which means higher surface tension in this case. So we made then other tries, and we tried to see if really the profile of the concentration it can be considered linear, which is a strong assumption in the first model, and also why not to take also a 3D equation for the temperature will permit us to consider also the case when the heating of the substrate is not uniform. But in fact, the problem of this trying are that they are not consistent. So we lost the advantage of the lubrication equation, the lubrication models, which assure that for a 3D model we have a 2D mathematical problem, and then we save a lot of time for the simulation. So the solution was to derive the model in a systematical way, and to include also the concentration equation in the frame of lubrication approximation. And now I start to present you the actual form of the model. So we start from the thin film equation, which is written here, and then for energy balance and equation for the concentration, which is written here. The boundary condition, the temperature on the low is constant. The temperature of the flux through the normal to the interface is considered to be 0, and also here it's for the temperature between the liquid and gas field, and here also the flux on the surface will be 0. Here are the non-dimensional variables. So in x direction we take L, which is much higher than D, and which I dimensionalize in z direction, and also for film height. For the temperature we take the momentum diffusion in the vertical direction, and okay, the other values are in non-dimensional form. These are the non-dimensional parameters, the most important: Marangoni number and Marangoni separation ratio. Also Schmidt number appear here, and if you consider disjoining pressure in order to avoid rupture, we need also some disjoining pressure, and we have also the Hamaker constant. So I cannot present all the calculations, so I write here that we perform a systematic expression of the basic hydrodynamic equation in the Longueweg approximation. We consider in the first order that the temperature is proportional to the height, so the vertical coordinate, and also till now it's standard for the lubrication approximation, and we derive a concentration for the equation, and also in the first order the concentration is proportional with height plus a function which will not depend on the vertical coordinate. And for deriving an equation for this function, we go in the next order of approximation, and that's a square. And then we show that we can replace this f to something which has more meaning, which will be the integral of the concentration on the vertical direction in one point. And we succeed to write the equation in the conservative form. Till now I work only with 2D, but the model can be generalized in 3D. So we succeed to write the H and phi, which is related with the concentration, in such a form, and how I write what means these fluxes, these two fluxes for H and for phi, and also which is the connection between this function f and the function theta, and the pressure and the surface tension in this case. So here is the disjoining pressure, the gravity, and the term due to the surface tension and the surface curvature. For the linear stability, we have the equilibrium values for H, and height, and concentration. We take perturbation, and then linearizing, we get such a system. Okay, A1, B1 depends on the non-dimensional parameters, and we consider a realistic system, let's say water isopropanol. So if the concentration of isopropanol is around 10%, then this Marangoni disjoining pressure, Marangoni separation ratio will be negative, and we are interested in negative value in order to obtain oscillatory behavior. So these are the parameters. In fact, phi will be in this case 0.21, but can be modified by modifying, and took as a parameter in the system by modifying the concentration of the two components. And here we obtain a very small value for psi for this codimension 2 point between oscillatory and monotonic. So we expect to obtain firstly from conduction at the beginning the oscillatory, and then if we increase the Marangoni number to obtain monotonic instability. So firstly will come into play the oscillatory, and this is a zoom in fact from the more complete diagram between the control parameters m and psi. So here we obtain firstly oscillatory and then monotonic instability to increase the temperature difference. And also here I represent instead of Marangoni, I took this epsilon, which means the distance from the threshold, and also playing with the film height. For small height, it's energetically favorable to obtain drops. For higher D, to obtain holes. Here it's something intermediately. There will be some strapes for not so high epsilon. And I will present you two simulations, one near the threshold and one a little bit. Okay, here are what means this region 1 to 3. So 1 means we have only oscillatory, only imaginary, so only complex lambda. For the real part positive. Here we have also real part, but the maximum is still for the complex number, and here the maximum is on the real part, so it will be mainly monotonic, but still we have some part with complex number. So here it's a 2D simulation. It's near the threshold, so epsilon is quite small. And we can see that, like in the simplified model, the movement of the drop is driven by the concentration. Here it's high concentration, but in both cases, the old model and new model, it looks like here means higher surface tension. So here it's lower surface tension, higher surface tension, which this will bring in the movement. The drop, these are time, a different time, the elevation, how it evolves. And here I put also the the current line, so the velocity field, and we can see here that, for example, here the liquid is tucked, and this elevation will decrease more here in the front, and here will grow, and this will be the mechanism. Here we have higher surface tension, here we have lower surface tension due to the concentration gradient, and this rolling of the liquid maintain this difference, and here higher concentration, here lower concentration, and this will be the mechanism will push the drop And also you can see the animation of this. I put higher speed in order to be faster. I don't have too much time. And also you can see the concentration field on the lower, and here the film height on the upper side. And if we start, also it's the question how vary this velocity of the drop depending of the separation ratio, and we obtain that for higher negative separation ratio we obtain higher velocity of the droplet. Now it's the case if we choose the initial, we choose some random, but if this random it's so that in one moment two elevation of the same magnitude appear in the system and move one to other, such a system can appear, and these two elevation will come into one single drop, and then this will be joined again in two drops which have the same shape like initial drops. So it's like, if you look at the velocity will be the same here, will be smaller here, and then again almost the drop will, after the nonlinear interaction, will move with almost the same velocity. And here is the animation. Maybe I will take a moment. So you can see that if the drops are on the same, almost on the same magnitude, so it will take a long time till one drop will win. And this is also 3D, somewhere not near the threshold. The system behave very tumultuous, let's say, and also the movement of the drops is driven by this concentration. In the left side is the height, and here is the concentration. And if you look at the movement of the drops, you see that it's driven by the concentration field. So everywhere is a white line in this direction will be the drop movement. And near the threshold you can obtain something which is oscillatory and very stable, rectagonal structures. Because of the time I will go also a little bit. So now it's almost
negative. Does it mean that
it's
compared
it's compared to the flat surface. So now will be some hypnotic build. I did not let it too much. And also we did simulation for the same parameter, like for one-dimensional, for narrow channels, which we take no flux on the lateral and the periodic boundary condition on the horizon. Okay, let's say now in this direction, and you obtain the movement of the elevation like in 1D, and also the case when we have two elevation, they meet each other and then they split again. So the same behavior also in these narrow channels. And finally I will present a case which is made of a little bit simplified model, so without gradient temperature, and initial state will be with separate components. So here will be one component, here will be another component. and some fingering appear in the system. And this is maintained by the difference of the concentration. If we have higher diffusion, which is the case here, we'll have the fingering will be not so pregnant. But if we increase, if S bigger means lower diffusion, so with lower diffusion, the concentration gradients are higher, and then the fingering phenomenon is a little bit more pregnant in this picture. I'm finished with my time, so I will go to conclusion, say that we derive the equation for a binary mixture in long wave approximation. For the thickness and temperature, we use a standard method. What is new is this new equation for the concentration in the order delta 2. And then we made linear analysis and the nonlinear simulation, which I already presented to you. So thank you for your attention.
Questions?
Let's see the energy functional again in the first or second slide.
Yes, this is more to see how we choose. But in principle, the model is a lot simplified. So here it appears also the sigma, which with a non-adimensionalization with right adimensionalization can be choose like 1, and here epsilon will be
It should be gradient and not rotation.
yes.
And so what is the
Yes.
rationale behind this polynomial?
It's only to be simple, a double well function with the left function will be corresponding to
So
the
there's
draining pressure. So this first model is in fact very, very simple, and we try to make it that simple, and this is only to see a little bit why we took like this. So finally we took also this Q1, Q2, the mobility is 1 and everything
It's
as
like
possible, as basic as possible.
the expansion about the wetting transition.
Yeah. This epsilon, it's related to the distance from the threshold also. But yes, in fact, you should look directly here to see that it's in fact it's similar with our model, but it's very, very simplified with the actual model, and still with this simplified model we can get a lot of the behavior which we obtain with the more complete and systematic model. Yes.
Well, H is very small. H should be small in your
Yes.
approach, and of course it is a distance relative to which other distance is considered to be small.
So to the lateral extension, so the wavelength in the horizontal direction.
Does it imply also that the gradient of H should be kept small in order for the model to make sense?
Yes.
What about
If you scale differently, so
I was a bit worried because
because you had these very steep profiles.
Yes, but it's if I represent on the same scale, will be nothing to see. So it's different scale in the vertical and horizontal. So
Non brilla troppo. Non brilla troppo.
it's let's say there are surface elevations
Like a wave.
like a wave.
In all these pictures, there's a length scale ratio epsilon interscaling of the picture. Whenever you see steep droplets in someone doing simple models, they are not steep.
Thank you.
No, but sometimes even the authors don't know.
I certainly didn't know.
No, I have
Just
seen
one
papers.
question, I probably missed it. What drives the instability? Your heat from below, or
Yes,
so it's like classic?
the energy comes from the heating. Yes.
Okay. So you're basically looking at the long wave type instability, because the shorter wave, which have a critical wave, Marangoni come at a critical wavelength, which
look
is
on the
usually not
long wave.
consistent with lubrication theory, right? So you just capture the long wave instability.
No, we return the speaker again.